Hello all, my name is Ashutosh Rastogi. I am a teacher by profession. My mission is to impart quality education for all. For that purpose I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Anyways, today in this particular lecture, we will try to give a brief introduction about the amplitude modulated systems. So these are the outlines. We are going to start up with the introduction. Then we will going to give the formal definition of amplitude modulation, which will be followed by the spectrum of AM signal, that is how much bandwidth or frequency ranges AM signal will going to occupy. And finally, we are going to conclude by discussing some of the standard, or you could say commercial AM radio band. So in our last lecture, we have discussed about the modulation and its needs. Modulation is the process of putting information onto the high frequency carrier for transmission, which is being called as the frequency translation. So this particular figure is showing the process of modulation. Here we will be having a message signal, which would have been called as your modulating signal or baseband signal, or you specifically say that it is your information signal. It will going to contain certain amount of intelligence. So that message signal and another signal that we are going to have your high frequency carrying signal, which is being called as your carrier signal. Both of these signals will get passed through the product multiplier or a modulator, and then finally the outcome of that product multiplier or modulator will be your modulated signal, which is going to have frequency shifted signal, that is low frequency signal will get translated over the high frequency carrier signal. So what is amplitude modulation? So the basic definition of amplitude modulation is being defined as the process in which the amplitude of the carrier wave, which is being denoted with this CT, is being varied accordance with the instantaneous value of the message signal MT. So here message signal would have been represented with this particular MT, and carrier signal would have been presented with this CT. So obviously what we are basically doing in this particular process is we will going to vary or change the amplitude of my carrier signal as per the instantaneous value of my message signal. So this is the key insight of the amplitude modulation. So this particular figure is showing the three signals, that is message signal, which is being represented as this MT. So this particular figure is basically showing your message signal, the signal that we wanted to transmit from one point to another point or from source to destination. This is the carrier signal, which is basically a high frequency signal, and with the help of this carrier signal we are basically trying to transport our message signal to the further distance. And this particular figure is showing the signal after the process of modulation. So this is basically the signal is ST, which is the signal that we will going to get after the modulation process. So this particular figure is basically showing the envelope, or you could say that it is the amplitude modulated signal. So the carrier frequency at the phase remains constant during the modulation process, just because we are only varying the amplitude of my carrier signal, and rest other features of the carrier signal will going to remain same, that is its frequency and phase will not going to change. An increase in the amplitude of the modulating signal causes of the amplitude of the carrier to increase. Since our carrier signal's instantaneous amplitude will only get altered as per the instantaneous value of my message signal. So as the variation comes into my message signal, that variations will get directly translated into the variation in the amplitude of your carrier signal. So both the positive and the negative peaks of the carrier wave vary with the modulating signal. So obviously if the complete variation in the amplitude of your carrier signal is being performed as per the instantaneous variation of my message signal, so obviously both the positive as well as negative peaks, both of the carrier signal will get affected as per the variation of my message signal. So an imaginary line connecting to the positive peaks and the negative peaks of the carrier waveform is known as the envelope. As we have discussed in this last figure, this imaginary line would have been called as the envelope, or you could say the signal that we get after the modulation process. So it is having both, that is your positive peak and negative peak. So this is basically, if you closely observe it, this is basically your carrier frequency whose amplitude will get altered. as per the instantaneous value of your message signal. So this is how we perform the process of amplitude modulation. So let us say MT be the time varying message signal. This is your message signal or the information signal that we are supposed to pass to the farther end. And this is your carrier frequency, which is basically a high frequency cosinusoidal or sinusoidal waveform, whose main responsibility is to basically reduce out the antenna height and facilitate our signal to transport to the farther distance. So let us say CT be the carrier signal, which would have been given as your AC cos of 2 pi FCT. So this is your high frequency carrier signal. This FC is basically representing the linear carrier frequency FC, and this signal would have been represented as AC cos of 2 pi FC. Let ST be represented the modulated signal and can be evaluated as, since we are superimposing both the message signal and carrier signal in the modulator and we are getting a combined signal. So basically at the output of the product multiplier, we are getting two signal component. One is the product multiplication of these two signals, that is your MT and CT, and second is your CT, or you could say your carrier signal. So ST will be equal to the product multiplication of your message signal MT and the carrier frequency cos of 2 pi FCT plus AC times of cos of 2 pi FCT, which is nothing but your carrier signal. Intentionally, I have omitted this AC, the amplitude of your carrier signal, although if I want, I can also put that AC times of MT cos of 2 pi FCT, but that amplitude is basically showing the strength of the signal. It doesn't has to do anything with the characteristics of the signal. That characteristics would have been definitely represented with the help of the frequency content of the signal. So if we want, then definitely we can use. Otherwise, for the sake of simplicity, we can omit that the amplitude of the signal AC. So simply ST can be given as ST is equal to MT plus AC times of cos of omega C. So the general expression of the AM signal can be given as ST is equal to MT plus AC cos of omega CT after taking the cos of omega CT as a common. So multiple times if we have to write it down, that cos of 2 pi FCT. So for the sake of convenience, I have just written as 2 pi FC as omega C. So if we want to evaluate its frequency spectrum, then we need to perform the frequency domain analysis. Obviously, without going through frequency domain analysis, how we could evaluate the frequency spectrum or the frequency band that it will going to contain that signal. So we need to evaluate the Fourier transform of the above expression. I'm talking about this particular expression. So let us say S of omega represent the Fourier transform of the modulated signal ST. So ST is your time domain signal, and in frequency domain, let us say we have represented as S of omega. C of omega is the representation of the Fourier transform of carrier signal CT, and M of omega basically represent the Fourier transform of the message signal MT. So in time domain, we are having this MT, CT and ST, whereas in the frequency domain, we will be having this S of omega, C of omega and M of omega. So now the Fourier transform of the carrier signal CT would have been calculated as C of omega is equal to Fourier transform of CT, and C of omega, that will be equal to Fourier transform of, in place of CT, we have just put it down this AC cos of 2 pi FCT. So the Fourier transform of cos of omega CT can be given as pi times of delta of omega minus omega C plus the delta of omega plus omega C. So this could have been easily evaluated. This is a standard Fourier transformation of your cos omega CT signal. What you could do is, with the help of Euler theorem, you can convert this cos of omega CT into e to the power j omega CT plus e to the power minus j omega CT by 2, and the simple Fourier transform of complex exponential signal can be given as pi times of delta of omega minus omega C. So by just doing simple calculation, we can evaluate the Fourier transform of cos of omega CT as pi times of delta of omega minus omega C plus delta of omega plus omega C. So now C of omega can be given as AC, since AC is the amplitude, so it will directly get multiplied AC times of phi delta of omega minus omega C plus delta of omega plus omega C. This is your equation number 2. So the Fourier transform of C omega would have been given like this. So this is your carrier frequency CT in the time domain, and this is basically its frequency domain representation. It is going to have two frequency component, that is your plus omega C and your minus omega C. So although this is your negative frequency component and it doesn't have any physical significance of having this negative frequency, this is a bookish concept, or you could say these negative frequencies existent on paper only for the mathematical computation. So this component is representing by this particular arrow, and this component would have been represented by this particular arrow. If we talk about the amplitude strength of these components, that will be equivalent to AC times of pi. So its amplitude is also equal to AC times of pi, and its amplitude also equal to AC times of pi. So this is the frequency domain representation of your carrier signal CP. So now the Fourier transform of message signal MT can be calculated as m of omega. This is the representation of the Fourier transform of your MT. So that will be equal to Fourier transform of MT. So MT signal would have been given like this one. It is your baseband signal whose maximum frequency component is your FM, and in this particular notion of angular frequency omega m, let us say it is having maximum frequency component, that is your omega m. So this is the spectrum of your message signal. So the frequency translated or shifted version of the message signal can be given as, since when we are going to product multiply this MT with the carrier signal, the message signal will get translated over the high frequency. It will get centered around the carrier frequency FC. So MT times of cos omega CT can be rewritten as MT times of e to the power j omega C plus e to the power minus j omega CT upon 2. So with the help of Euler theorem, we have rewritten as cos of omega CT like this one. So when we are going to multiply this MT times of e to the power j omega CT upon 2 plus MT times of e to the power minus j omega CT by 2. So now the Fourier transform of the frequency translated message signal MT can be calculated as m of omega, that will be equal to Fourier transform of MT cos of omega CT. And we know that whenever we are going to multiply the exponential signal to any signal, that signal will get translated, or you could say its frequency will get shifted via that exponential term. Likewise, m of omega, that will be equal to Fourier transform of this one. So MT cos of 2 pi omega CT can be written as in terms of Fourier transformation, that is half of m of omega minus omega C plus m of omega plus omega C, where m of omega is basically representing the Fourier transform of your MT, and that Fourier transform of MT, or you could say the frequency domain representation of your MT, will get shifted from this frequency omega C. So it will get centered around your omega C. This is your third equation. So here in this particular figure, we are basically representing the frequency domain representation of this particular signal. We will be having two bands. One is your this upper sideband and another one is your lower sideband. If you closely observe that, its frequency is your omega m, and it will get shifted via this frequency term omega c, which is represented by this m of omega minus omega c represented by this particular term, and m of omega plus omega c represented by this particular. So now from the general equation of AM, we can write the expression for spectrum of AM signal, such as S of omega will be equal to half of m times of omega minus omega c plus m times of omega plus omega c. So this is the first component, which is basically first component of your ST, which is nothing but the product of your message signal with the cos omega CT term, or you could say carrier frequency term. And second term is the carrier signal. So carrier signal's frequency domain representation can be given as AC times of pi delta of omega minus omega c plus delta of omega plus omega c, as we have discussed in the previous slides. So this is our message signal MT, whose frequency domain representation can be given as like this. This is your band limited signal, That is, this particular signal will not going to have any frequency term greater than omega m. So this is your band limited signal. Second is your carrier frequency. Since it is only having single frequency, so these frequency terms or frequency domain representation of this carrier frequency signal can be given like this one. It is going to have two frequencies. One is positive, that is your plus omega c, and one is your negative frequency component minus omega c, which is nothing but your virtual frequency or negative frequency, doesn't have any physical significance. And in the third figure, we will be having this modulated signal, or you could say this envelope, and the frequency domain representation of this envelope can be given via this particular figure. So this S of omega is represented by this particular figure. So it will again going to have this carrier frequency signal AC pi times of delta of omega minus omega c plus delta of omega plus omega c. So these terms are basically representing the carrier terms, this purple arrow. And if you closely observe that, this whole message signal will get translated or shifted in the roundabout of your omega c. So this is the same signal. These signals and these signals, these are the same signals. The only variation is that this lower frequency signal will get translated towards the high frequency signal, which will going to serve the purpose of modulation, which will going to basically reduce out the antenna height, as well as it allows us our signal to travel longer distance. So this is the spectrum of your AM signal figure. So this is showing your spectrum of message signal in linear frequency term. So in the previous figure, we have used that term omega m and minus omega m in terms of linear frequency. That MF can be represented as this particular figure, which is your band limited signal. That is, this particular message signal will not going to contain any frequency larger than your FM. So this is the spectrum of your message signal, and same message signal will get translated roundabout in the carrier frequency. So this signal will going to get shifted at plus FC and minus FC. So again, if you are talking about the frequency translation of this particular signal, that the FC is the central carrier frequency, and that message signal will simply get translated towards this. So this particular band, if you closely observe that, FC and FC plus FM. So this is basically a band which is called as your upper sideband, and the frequency ranges or band that is lying between FC and FC minus FM, that is called as your lower sideband. If you closely observe that, both these bands, that is your upper sideband and lower sideband, will going to contain the same message signal, or they are the replica of each other. So now few special points about the spectrum of the AM signal. What are they? The frequency spectrum of AM signal contains three parts. Number one is the component of the carrier frequency FC. We had already seen in our last slide. An upper sideband whose highest frequency component is at your FC plus FM. And if you are talking about your band, then that band will lying between FC to FC plus FM. And the lower sideband whose highest frequency component is at your FC minus FM. And if you are talking about lower sideband, then that band contains a range of frequencies that is from FC to FC minus FM frequency band. So because of the two sidebands and the carrier signal in the frequency spectrum, it is often called as your double sideband with full carrier. In the abbreviation terms, we could write down as your double sideband full carrier signal. That is double sideband just because it is containing two sidebands. Number one is your upper sideband and second one is your lower sideband. And since it is also containing carrier signal, so that is why we are calling them as your double sideband with full carrier. So the information in the baseband or the information signal is duplicated in the lower sideband and the upper sideband, and the carrier conveys no information. This we had already discussed, that the lower sideband and upper sideband are basically the mirror images of each other, or you could say that they will going to contain the same information signal. So basically same message signal will get duplicated in the lower sideband as well as your upper sideband. It will also going to contain the carrier signal which conveys no information. This is simply a single frequency, or you could say single frequency component high frequency signal. So the negative frequencies appeared in the spectrum analysis due to the exponential representation of Fourier transform. So due to for the exponential representation only, we'll be having positive as well as the negative frequency. This we had also discussed, such as the basic definition of frequency is nothing but number of oscillations per unit time. And if you are talking about any negative integer or negative number, it does not provide any physical significance. So they are just being used for mathematical convenience. As for real function, and these negative frequencies have no meanings. But effectively, when these negative frequencies are combined with the positive frequencies, they will going to form certain real number, which is quite necessary for the analysis of our signal for complex exponential. So now we're going to discuss the spectrum of AM signal. So bandwidth of the signal can be given as any generalized signal. The bandwidth of any generalized signal can be given as the difference between highest frequency component it will going to have minus the lowest frequency component it will going to have. So in case of AM signal, the bandwidth also given with the same specification, that is your Fmax minus Fmin. Here Fmax is representing the maximum frequency component of your modulated signal, and Fmin is basically representing the minimum frequency component of your modulated signal. So where Fmax and Fmin are representing as such. So as we know that maximum frequency component from the figure or the frequency domain analysis, we have find out that the maximum linear frequency component in our spectrum of our AM signal can be given as your Fc plus Fm. This is your maximum frequency component, and Fc minus Fm, that is your minimum frequency component. So when we're going to subtract this, Fc plus Fm minus Fc plus Fm, that comes out to be twice of Fm. So this basically shows that the bandwidth requirement of FM signal will be equal to twice of FM, where FM is the maximum frequency component of your message signal. So please keep in mind that it doesn't have any term of your carrier frequency. So the bandwidth requirement before modulation and after modulation, in both the cases, bandwidth requirement will going to remain same. Now this particular figure is basically showing the standard, or you could say the commercial AM radio band. So, so the frequency ranges between 530 kilohertz to 1700 kilohertz would have been allocated for AM signal broadcast. So individual channel bandwidth will going to have this 10 kilohertz of bandwidth. So if we closely observe that, and if we need to find out that how many maximum number of AM broadcast channels can be possible via these particular frequency ranges, we can easily evaluate is the complete bandwidth can be evaluated as 1700 kilohertz minus 530 kilohertz. So that turns out to be 1170. And if we do not perform any sort of guard band, and in that particular case, and if we are assuming that the 10 kilohertz bandwidth is allocated to a single channel, then in that particular case 1700 minus 530 kilohertz divided by 10 kilohertz, that will be the total number of maximum total number of AM broadcast channels that are possible by these standards. So hopefully you will get the better insight about your AM radio frequency bands along with amplitude modulation. So in case of any doubt, you can ask me in the comment section. I'll try to solve it out as soon as possible. So these are the references. Thank you very much for your patient hearing.